Actually, I remember thinking, seeing kind of yesterday was basics of deep learning. Today is advanced deep learning. And it made me think like, wow, we're moving fast. It's like, what is tomorrow? Is this a Nobel Prize? Like, I'm ready. Like, but yeah, okay. I think maybe it's a little bit better to think like today and the rest of the lectures are going to be kind of specialized topics, right? So yesterday gave kind of the foundations in deep learning. These are these are kind of principles which apply into all sorts of research areas. Now we're going to dive into a few of the more specific research areas, and tomorrow, next day, you'll also see kind of other kind of specialized topics which will refer to the ideas that we mentioned yesterday, but which are their own kind of isolated research fields. And the plan for my lectures today, I have 4 talks. They're all pretty much independent from one another, and they actually change the topic quite a bit. This one and the one on meta-learning are a little bit longer. And then there's one on interpretability and one on GANs, which are a little bit shorter. So we'll divide up the day this way. I'm not going to talk at you the whole time. I have a list of exercises that we can try to break into groups and solve together. So yeah, I think that's it. And Bayesian deep learning, this is going to have some overlap with what Dovan is going to talk about a little bit later on graphical modeling. So you'll see that they're a little bit complementary, the topics. Okay. So what are we going to try to do? The first, there's a little bit, again, I want to trace some of the historical connections, right? Like just like yesterday, we started with logistic regression, and then we got up to ResNets, right? Today, I want to start kind of the foundational, like what is Bayes' rule, all the way up to what are people doing in Bayesian deep learning today. I want to add a few kind of example models, right? So this is something that I think is handy because when you read a Bayesian deep learning paper, they will often present everything in the most abstract form so that you can apply that algorithm in as many situations as you can. But then to really understand what's going on in practice, it's helpful to have a few special examples in mind so that you can take this very big abstraction and then apply it to this kind of case that you know really well and see how does this general algorithm work in the specific case that I care about. So hopefully we'll add a little bit to your kind of personal catalog that every time you see a new algorithm, you try understanding that algorithm in context of these simple examples that you already understand very well. And then yeah, I want to get past a little bit of the like high level, uncertainty and modeling. I want to be able to show you like what is the math behind these and like what is the code, so that you have some confidence that if you need to try experimenting with these methods or if you want to try extending them, you have the essential foundation. Okay, that's the plan. So I start 2 papers from 1990, probably before most of you were born. And I think that they're both really foundational papers in modern machine learning, but then they're totally different communities. And the people who were writing them, they probably weren't even aware of each other's work at the time. So this one on the left, it's by Jan LeCun on handwritten digit recognition. So this is one of the earliest, if not the earliest, MNIST paper. And it's just proving that you can use convolutional neural networks, not deep learning yet, but convolutional neural networks, to predict digits. The one on the right, this is the Gelfand and Smith paper, so maybe you don't know this so well, but in Bayesian modeling, there's a method called Gibbs sampling, and up until this paper, Bayesian modeling, or like Bayesian probability was kind of a more, it was like a theoretical kind of philosophical investigation. It wasn't considered something that you could actually do for data analysis. And then this paper said that, well, if you use this certain kind of try to avoid doing some of the math and instead use these very intensive computation, you can actually do Bayesian analysis in practice. A few people had floated around this idea just around the time. So there was like the data augmentation people, there was the Gieman and Gieman paper around the same time. But this paper was kind of so good in its exposition that the whole community started paying attention to Bayesian analysis, right? And they began realizing like, oh, this is something we can do. And it's kind of interesting to notice the similarity between the two in the sense that they're both about automating things, right? So in the MNIST example, what you're automating is this feature extraction, right? Usually if you're doing image analysis, if you're doing classification, you need to design like edge detectors, you would need to design kind of very specific ways to extract meaningful features from the digits. But then with CNNs, that's automated for you. You don't have to worry about it anymore. And the same thing in this Gibbs sampling paper. Kind of before, if you wanted to do Bayesian analysis, you would have to do all these integrals by hand. And that's, you can only solve a certain class of problems by hand, and it's really expensive, like human time-wise, to do that for every problem you want to solve. So being able to do this computationally was a major advance, right? So they were both, like they share this kind of computational aspect. But then there's an interesting, like, major difference is that the kind of handwritten digit recognition paper, they really only care about classification, right? They're not giving you any sense of kind of probabilistic inference about what you're classifying, right? You don't have any sense in which, like, this is my posterior over image labels for this example. It's more of just like an engineering problem. Versus the Gibbs sampling paper, it's all about how do you understand uncertainty in some system that you're modeling, right? So there's full probabilistic descriptions of the objects that you're studying, right? So instead of just classifying something, you would get like a whole bunch of probabilities about this is how sure I am of the different classes, right? So there's this tension between just engineering, solve the problem immediately without worrying about quantifying uncertainty, versus kind of this purely or like inferential point of view, but which might be a little bit less rich, right? Like Bayesian analysis, as complicated as this was at the time, it was not nearly as like engineering intensive as some of this CNN work, right? So on the one hand, they're both similar in that they're using computation to automate difficult things, but on the other hand, they have this difference in priority. And a few years later, there's a very important paper called The Two Cultures by Leo Breiman. So I recommend you check this out just as a matter of kind of historical knowledge. And it kind of really delineates this split in the machine learning literature where some people started focusing entirely on inference and kind of building simple models but having very rich descriptions of them, whereas other people kind of gave up on the chance of having rich descriptions and just wanted to have complicated models, right? So those are the two cultures. And kind of the exciting thing that's happening right now, in the last couple of years, is that these two cultures are kind of meeting at a few points, right? So, like, of course, you want to have things that are kind of best of both worlds, right? Like, you want to have a complicated model, but you also want to have some description about how certain are you of your predictions, right? And more than that, right, you want things to be fast, and you want things to be automatic, right? So this seems like a perfect chance to blend Bayesian analysis with deep learning, right? Deep learning we saw yesterday is this kind of very modular way of working. It's easy to iterate very quickly across a whole bunch of different architectures, a whole bunch of different families of functions, because you can always use backpropagation, right? You can always use gradient descent. So in that way, it's like very easy to develop and very rich, but it doesn't give you the kind of probabilistic inference that is often useful. So if you can combine them together, if you can have like fast, modular machine learning creation, while making sure that those components give you something that's scientifically valuable rather than just like an engineering tool, then this is what kind of would be useful for a lot of people, right? Okay. So before getting exactly into how that unification takes place, I think it's useful. This is how I think of every single machine learning model. Like it doesn't matter who's designing it. There's always these three questions you have to ask, right? The first is, what is the model class, The second is what is your evaluation criteria? And then the third is what is your search strategy? Right, so kind of graphically, the way I visualize this is kind of f, this is some class of parameters or like class of functions where like each point in this f would be kind of one fitted function that you've, this is your fit that you would use in the real world, right? There's a huge kind of class of functions, like yesterday, the kind of layer, like the mixtures of logistic regressions, right? There are many kind of versions of those mixtures of logistic regressions. It's hard to find one that actually fits your data, right? So how are you going to find one that fits your data? You need two things. First, the evaluation criteria, that's, you need to have some notion of, is this function fitting my data, right? So like that's how I think of this on the right. It's like I have this green is like the truth, or the points are like the truth, and then red is kind of my approximation. And then you need to have some sense of, okay, is my truth close to my approximation? And there are many ways to measure this, right? You can do sum of squared error, you can do sum of absolute error, you can do all sorts of decompositions, right? So you need to have some sense of, are you doing well or not? And then finally, even if you have some way of comparing different fits, you need some way of getting to the one that you're going to use at the end, right? So either it's a gradient descent thing, or if you're doing decision trees, like maybe it's your sequence of splits, right? But no matter what machine learning algorithm you're doing, you need to have some sort of search strategy. It's either a formal mathematical thing or a very heuristic, like I'm going to enrich this part of the model, but then decrease this part of the model, right? But if you have this, then you can kind of understand any machine learning model that you come across. So how does this look like in Bayesian deep learning in particular? So in the kind of model class, this is usually very explicit, right? In other areas of machine learning, the model class can be kind of like a heuristic definition of like trees that partition certain space, right? It's different in Bayesian deep learning or in Bayesian analysis in general. You write down a specific probability mechanism, whereas I first sample this random variable, and I sample these random variables, I combine them in some way, and that's going to be my description of all the possible functions that I can fit, right? So some combinations of random variables, right? What is your evaluation criterion? So again, because we are thinking probabilistically, you're going to use probabilistic quantities, right? So far we've been talking about things like maximum likelihood, right? So maximum likelihood would be kind of one probabilistic evaluation criterion, right? We can choose the function fit or like the sigmoid, which has the highest likelihood, right? There's a point at the top of the curves in the coin flipping example, right? But then there are other ways to do it, right? So it doesn't have to just be maximum likelihood. So today we're going to actually talk a bit about something called the evidence and the evidence lower bound. So yeah, these are like, when you're thinking about Bayesian deep learning, when you think about evaluation criteria, try to think about like what are the probabilistic quantities that we're going to compute to say whether a fit is good or not. And then finally, what is the search strategy, right? So this is a little bit more complicated in Bayesian learning than in most other methods, right? But then, yeah, you'll see that, yeah, the main difficulty is going to be that we want to actually have kind of full posterior estimates potentially, right? So these are a few common methods. We'll focus just on variational inference today, but I want to include these other two just in case you're curious. There are other ways to do Bayesian inference that aren't what we're going to be talking about. Okay, so that was the view from the top. Now let's start at the beginning, right? So I think you all talked about Bayes' rule in one of the earlier lectures. The way to think about it is just you have some belief about the world. That's P of theta. Oh, okay. Oh, no. Okay. Yeah. Sometimes I wonder, like, we pretend we're making all this advanced technology, and then it's like, I have no idea how this works. but okay. So maybe it's using phase rule, probably, who knows. So, okay, again, this is just, you have some belief about the world, you encode that in P of theta. You observe some new data, X. And then kind of the right thing to do is to update your understanding of the world. That's P theta given X, right? Kind of, this is as opposed to like non-scientific thinking, right? If you think about what is the definition of non-scientific thinking, it's like you have a belief about the world, you get data that's contrary to that belief, and you don't change your mind because you're fixed your beliefs about, like that would be kind of non-scientific thinking. Bayesian analysis kind of quantifies what is scientific thinking. Okay, and then I believe you saw this example too. So this is kind of the canonical beta binomial conjugacy example. The idea is you would begin with some prior over what you think the probability of heads is going to be for some coin when you're flipping a coin. Then you flip it a certain number of times, and then you kind of move that prior towards a new peak. So this is after seeing a certain number of runs of a coin with probability 0.2 of heads, and then it's moved, it's concentrated information around 0.2. And actually, if I had simulated more and more coin flips, it would get narrower and narrower because it gets more and more sure that it's at 0.2. Right? So this is, you have a formal way of saying, I'm accumulating evidence, and as I accumulate evidence, I get more and more sure of my estimate. Okay, I just wanted to include code because it's nice to know that this is not just a purely mathematical construct, right? And it's also nice to see that, it's nice to see an example of this in code because in this particular case, we can work out the posterior distribution in closed form, right? You can show that the posterior in the beta binomial model is still a beta. But in a lot of cases, you can't do it, right? So in those cases, you need to resort to doing some sort of computation. And this kind of gives a simple example, right? So this is using a library called Pyro. It's built on top of PyTorch, which you know from yesterday. And just what's going on here, nothing too crazy. I'm defining my prior and likelihood here, basically. So these are the parameters of my prior. So this is actually, I'm starting off thinking that it's around 0.5 with relatively high confidence. This is sampling, this is saying, this is how you sample from the prior, right? I'm just drawing a beta with those parameters. And then this is just kind of a complicated notation for saying that I'm going to draw n Bernoullis with the probability p. And I'm going to stack all those observations in an object called data, right? So it's basically a way of linking this observed numbers, the data, with some sort of model, right? So here's the data, here is your model. I mean, this other stuff is just like reshaping things, and this is telling you that these are independent, right? Because they're independent coin flips. So okay, it's nice that you can define a model, but what you really want to be able to do is define a posterior, right? Or like to identify your posterior, right? And what's kind of cool here is that you don't even need to tell this package, like these are the closed form formula for the posterior. What you can do, and it's a little bit subtle. So let's start at the end, actually. You're defining this object which is saying, draw from a beta distribution with parameter alpha q and beta q, where I don't tell you what alpha q and beta q are. Right? So this is just a large family of beta distributions. Some of them are concentrated near 0, some of them concentrated near 1. They're all over the place. But then, yeah, you're just going to define this function called guide, which is taking, which is going to return like some member of this large family of beta distributions. All this stuff is doing is saying these are kind of the plausible values of alpha and beta. Right? So all it's doing is it's constraining it, and it's giving an initialization value. But when you are going to search for what is a good approximation of my posterior, or what's a good posterior, it's going to try fiddling around with these alphas and betas until it finds one that's close to the truth. Right? So this is... do I have any more on this? OK. The last thing I want to say about this is this is kind of cool because you don't have to do any integrals. And so what you would end up doing after this is you just write some a pyro dot variational inference of my guide function and my model. And it's going to, my guide function, my model, and my data. Right? And it's going to find one element of that large class of guide functions, which is very close to what you've seen in the data. Right? And if you run this on this example, it's interesting. It doesn't get exactly the true posterior, because we know the true posterior in this case. We can write down the formula. We can get the alpha and beta for the posterior in closed form. It will try to run stuff. It will run for however many iterations. It will give you an alpha q and a beta q. And it's usually close, but not perfect. Right? So this is kind of the thing that you on the one hand, you gain that you don't have to do any math, and it's super fast. But on the other hand, you lose that it might not be totally accurate anymore. So this is the kind of trade-off you'll often have to navigate in any kind of Bayesian machine learning these days. Right? Some things might be more convenient, computationally a little bit easier, but statistically you might lose something. So you need to figure out that trade-off on your own. Right? It'd be nice if there were a little bit more guidance about it, but that's still research. OK. So that's a little bit about kind of how we're going to aim to do this sort of posterior inference. We want to do something a little bit more automatic, right? A little bit less math intensive. And actually, the thing that Pyro is doing is the next section is variational inference. So we'll get there. But before then, I want to introduce latent variable models, because kind of the place where variational inference really shines is when you're trying to do some sort of inference with latent variables. So let me define what that all means. OK, so kind of one way to think of it is in a lot of real-world data distributions, right, there's this kind of underlying really meaningful concept which you don't observe, right? You only observe data which are kind of some sort of downstream transformation or a noisy version of that underlying concept, right? And then you need to kind of backtrack to figure out what were those underlying concepts, what was that underlying source of variation that was really meaningful, and see how that connects to the data that you actually have, right? That's kind of abstract. It applies very generally, but maybe a useful example to keep in mind whenever you think about latent variables is the mixture of Gaussians model. Right, so what is the mixture of Gaussians model? Just these three lines, or this picture, right? So what's going on in these three lines? First, I draw a whole bunch of means. So here, let's say I draw 3 different means from some prior distribution. My prior is going to be from some normal. So most of the means are going to be around 0, right? Zi, this is, I have a probability vector, like a size 3 probabilities, right? And this is just telling you, do I draw from one of the Gaussians or the other in my actual data, right? And then finally, I draw like a specific noisy version around the kth mean, right? OK, so this is still a little bit, this is the math, but I think it's easier to understand if you just draw a picture, right? So what's happening in the picture? First, I've drawn 3 of these mu's. So these are the 3 mu's. I'm kind of fixing some sort of covariance for the sigma case, but I'm not actually sampling them here. I just assume that for each of these k means that I draw, I'm going to have some like circle or ellipse, right? Zi, this is going to be this big matrix. I'm going to have 1 row for each of my observations, and each column is going to be one of the possible mixture components, so 1, 2, or 3. So first I have, in this first mixture component, the first observation is going to be the first component, so I have an observation in that first component. And what I mean by the observation is I first get to that mean, and then I add this sigma k variance, right? Or I draw from that sigma k variance. So that's how I get my first observation. The next observation, okay, it's also zi equals 1, so I draw another one from that same mixture component, right? And then maybe, oh, okay, zi, I'm going to draw it again, but then since this is random, I get the third component. So when I get the third component, I look at a different, I get a new kind of place where it's close to. And then you just continue doing this a whole bunch of times, and eventually you start observing data that looks like this, right? You have kind of clusters of data around one mean, clusters around another mean, and at the end you have this big matrix that's kind of encoding which component did each individual data point belong to, right? So this is just like the graphical way of understanding this set of equations. Okay, makes sense, the setup? Any questions? Okay, now the issue is going to be that in the real world, we don't actually have the zi's, right? You only observe data like this, except you don't have the colors saying that they're different mixing components, and you are never allowed to see this zi, right? So this is what I mean by like you have an abstract concept, but then you need to back your way back into that abstract concept from your data, right? So like when you look at this, kind of, even if I didn't have the circles there, you'd kind of be able to guess, like, it looks like there are 3 different clumps, and I can try to separate my data into the 3 clumps, and maybe that helps me understand the source of my data a little bit better, right? But you need to be able to do this in code somehow. And okay, so now that we've seen this one example, it's kind of nice to see there are a whole bunch of other examples where this sort of thinking applies. Yeah, it's too bad. There's a reference for Shakir Mohammed's thesis was on this topic. Yeah, and he has a whole bunch of kind of beautiful applications. But kind of the main point I want to say kind of in this kind of general, besides just pointing you to the names of things, is that we're thinking about the zi's as being kind of categorical things, right? So like you can belong to one of these 3 different clusters. But in a lot of models, including LDA and exponential family PCA, you have more continuous variation, right? So instead of belonging to one of these K classes, you kind of vary in this low-dimensional representational space, and that manifests itself in kind of smooth changes in your high-dimensional observation space. So kind of a canonical example in computer vision would be, let's say like I have a whole bunch of images, and across those images I have differences in the lighting, right? So some of them are very, very bright, some of them are very dim, right? You imagine that there's some zi, instead of being these k categories, you have a one-dimensional axis, which is like the brightness axis in your latent like concept space. And then when I pick some zi, and then I generate a high-dimensional image from it, the kind of overall pixel intensities depend on what that zi was, right? So if I'm in the part of the zi space which has very high illumination, then the image I'm going to generate from it is going to have very high illumination. Versus if I'm in the part of the zi space with very low illumination, it's going to end up becoming a very dim image, right? So that's the sort of thing like an exponential family PCA would be really great at, because it allows for this kind of continuous zi variation. But I think for just understanding kind of the basics and like getting some intuition about when you see a new algorithm, how does it work on mixture models, think about like discrete k. I think it helps. Okay, so this is just in closed form the entire complete data likelihood for the Gaussian mixture model that we just wrote down, right? So what do I mean by the complete data likelihood? The complete data likelihood is the likelihood if I knew the mixture assignments, right? So there's this big matrix of z's, right? In the real world, I don't know it. but then assume you knew it. If you knew it, then you can write down the probability of the data that you observed, right? And it's actually not too bad, right? What you do, kind of first, kind of ignore the indicator thing. What this inner part, this is just the probability of a data point given that you know which cluster it belongs to, right? So kind of like, if I knew that this point belonged to this cluster, I can evaluate its likelihood, because this is kind of a Gaussian on top of this circle. And then since the likelihood is decaying like this, I would know the height of that decay, and that would be my likelihood for this point. And I can get the likelihood for every single point if I knew that it belonged to this component. If I didn't know it came from that component, then it's really tricky, right? Because maybe it's actually from that one, and it decayed this way, so you wouldn't be able to know. But let's assume that you actually know the components, so that you can actually write down all these likelihoods. And what's the rest? This is just saying, you are you want to multiply those likelihoods only when you actually are coming from the kth class, right? So if this xi didn't come from class 1, you wouldn't want to multiply the likelihood of that point coming from class 1, right? So this is like a notational trick, right? The notational trick is write down all the likelihoods multiplied by each other, right? So in this picture, for this point, I would write down the likelihood assuming it came from this cluster, and then I would also write down the likelihood considering it came from this cluster and from that cluster, right? So I write down all of them, but then raise some of them to the power of 0, right? So raise all but the one that it actually comes from to the power of 0, and when you raise something to the power of 0, it becomes 1. So it's like it didn't even exist, right? But it just makes it much easier to write down notationally, right? So that's all that's happening here, is I wrote down all the xi's across all the different k's, so I'm taking a product across all the k's for each data point. But then I zeroed out if it didn't actually come from class k, right? That's what this indicator does, right? And then the pi k is just factoring in some of the classes are more likely than others, right? So you want to give higher likelihood for the classes that are more common, right? Now, the log of a product is just the sum of the logs. That's all this line is. And this is just expanding out what that Gaussian density is in closed form, right? It goes on a little bit more, but not that much more. And okay, this seems a little bit messy, but in the grand scheme of Bayesian models, this is a pretty tame expression. It's tame because it's actually just a quadratic in x, right? So whenever I have x times x, that's the most complexity I ever have. So that's pretty easy to work with, actually, in a lot of situations. Okay, now this is going to be the issue, right? So we have a nice expression for the likelihood if I knew the z's, right? So you can imagine that if I knew this z, then I can figure out the mu's, which optimize my likelihood, right? It's I have this expression. I can actually just differentiate everything with respect to each of the mu's. And I can differentiate everything. Yeah, I guess that's the only parameter here, is this mu, right? So I could figure out the best mu's given my class assignments for each of these data points, right? What this would look like in the picture is, since I know where each of these points came from, I know which component it came from, I would just say, okay, the average of all these components, that's going to be my estimate of the mu for that class. And then versus the average in this component, that's going to be my mu for that one, right? So you could actually figure out your parameters, mu, very easily, right? But then you don't actually know the z's, right? So what do you have to do? You would imagine having to sum over all the possible, or consider all the possible configurations of the z's, right? And then you'd have to update your mu, your means, kind of factoring in the likelihood of each of these different configurations, right? So that's what this formula is saying, right? P theta of x is the likelihood of the data if I didn't see x, or sorry, if I didn't see the assignments, right? It's just the likelihood of x, the observations. Since the only way I have of writing down the likelihood is by introducing my mixture components, I need to write down this kind of complete data likelihood. The only way this expression stays valid is to do log of the sum over all the z's, right? This is just this is just marginalizing, right, in probability. If you want to figure out the probability of one variable, but you have a joint distribution over two, you marginalize out the other one by summing over all its possible values, right? Now, that would be okay if the number of values in this sum weren't really large. But then think about the number of ways you can try to assign these points to different clusters, or like to the different mixture components, right? Kind of, for each of these points, you have 3 choices, right? And then you have to do this across all the points, right? So you have like an exponentially growing number of configurations that you have to consider, right? Like you can actually just try writing out. So like first I have just the first point belonging to the first component, and then all the rest of the points belonging to the second component. Oh, but then now I can do like the first 2 data points coming to the first component, and then the rest of them coming from the second component. And then you can just kind of iterate through all these different kind of configurations, and then you can start zeroing things out, and then yeah, it grows really, really quickly. So you can't actually do this sum. So we need to come up with something a little bit more clever. Okay, so like, you would think that you're stuck at this point. You would think that there's too many terms to do the sum over, there's no way I'm actually going to be able to do maximum likelihood. But people have been thinking about this for a long time, and there's a really kind of a problem-solving that strategy that comes up in a lot of situations actually is when you think you're stuck, give yourself some more room. And the way you can give yourself more room is a little bit unintuitive, but you add more complexity to your model, right? Or you add more complexity to your derivations, right? And once you add that complexity, then it gives you some more space. And once you have the space, then you might find a way forward, right? So that's what we're going to be talking about now. So, okay, this is maybe this, and one other slide is like the most math-heavy slide. But let me walk through how do you actually add complexity, right? Kind of it's related to the guide function idea, right? Let's just make up some other distribution Q, right? It doesn't necessarily have to be related to my observation distribution at all, right? But I'm making up some Q of z given x. This is going to be something like a guide distribution in the end. And what I do is kind of this log p theta of x, that's the thing that I want. It doesn't have anything to do with z at this point, but I'm going to consider this kind of distribution over the configurations z. And I can just, the first equality happens because there is no z, right? If I am taking an expectation over a quantity where that randomness doesn't even exist, then that's fine, right? Like it's as if you hadn't taken the expectation in the first place, because that variable is not even there. So like, okay, that's how you can get this first equality. But now you get clever, right? Now you introduce z back in, right? So what this expression is doing, so okay, first of all, this is basically just Bayes' rule in reverse, right? Or, I mean, you can also think about it as like z given x is z and x divided by x, right? So if you rearrange the formula, then you just get to p theta of x, right? So again, it's just like I started with something simple as p theta of x. I made it a little bit more complicated, but now I have z, right? So now my expectation actually matters, right? I'm doing an expectation over something which has the configurations in that expression, right? So my distribution over q now matters. It's not like the first expression where like I could choose any q I want and the numbers that I get on the right and left are going to be the same. Here, as I change different q's, my numbers are going to vary a little bit, right? And it's actually worth thinking a little bit about what is like how you reason about this quantity, right? So think of it as q is giving some probability to each of the configurations, right? So like a very simple queue, maybe it thinks all of the points come from mixture component 1, or all of the points come from mixture component 2 with equal probability, and all the other exponentially number of configurations have 0 probability. So then I'd just be averaging over 2 configurations, and I would calculate the likelihood assuming those 2 configurations, and I'd add them together, right? That would be kind of one possible choice. So what that's doing intuitively is it considers all these actual kind of likelihood computations for fixed configurations, and then combines them in some way that the way it combines is it assigns more weight to the configurations that it thinks are more likely, right? So if it finds some configuration of the Z that looks like something I might give rise to the data, then maybe you assign more weight to those configurations, and then you factor that when you take this expectation. Okay, but we'll see more examples of this later. Okay, so here's the second kind of clever thing. So this is a proof with several clever steps. I multiply and divide by 1, right? So you can always do this, right? Q divided by Q is 1, so I can always multiply by 1, right? And now you just rearrange terms. This line actually isn't that clever. This line is just, I need to know the definitions of what the KL divergence is. But is it clear what would happen? Like this last term is like a KL, because it's expectation over Q of Q over P. That's like the KL divergence between Q and P. And, and this previous part decomposes into expectation of this log likelihood and this kind of second KL term. And the difference between these two KL terms is one of them is the difference between Q and my posterior, like the true posterior of Z given X. And the other one is a KL divergence between Q and my prior over configurations Z, right? So at this point, Q is just some arbitrary guide function. Okay, thank you. Okay. So now another kind of general lesson. Whenever you see complicated expressions, try to interpret them, right? Actually, I probably should have just drawn a picture, because I think you can understand each of these things using pictures too. Maybe this is an exercise for you later. Like the distance between two distributions, you can represent that geometrically, right? You just draw two distributions and you look at the distance between them. That's what the KL divergence is. Log likelihood, like we drew a few different log likelihoods for the beta binomial situation yesterday. You can draw log likelihoods for all sorts of functions. And then here, like the expectation over Q is like, I have a whole bunch of these likelihoods and I'm averaging them together in some way. And okay, so try to draw pictures for them. But for now, we'll settle with some sort of qualitative description for what each of the terms is, right? So the red, this is an expected reconstruction error, right? So why is it called the reconstruction error? It's Z is giving some sort of assignments to each of my points, and then X is like the data that it is generated from that configuration, like from that particular assignment, right? So like maybe one way to understand this is like in this Gaussian example, this configuration has very high probability. If I'm kind of assuming that all these points in the bottom right belong to one class and all these points on the top left belong to another class, that's like the reconstruction is very good. Because when I generate points from that configuration, I would expect to see something just like this. But then you could have also, let's say I had like randomly assigned the ZIs across these points, right? So that like instead of the colors being nicely separated right now, what if I had scrambled all the colors for those points? You can still compute a likelihood, but it's just the configuration that you'd be observing is a little bit less plausible, right? Because like, why would you have the gap between these groups of points if they actually they were all being generated from some mean that's in between all of them, and the three colors are all kind of mishmashed with each other, right? So like the reconstruction error would be higher because it's just not a plausible configuration anymore, right? Oh no, okay. The second term, the KL divergence between Q and P of Z, right? The interpretation here is my guide function, this is like some arbitrary distribution over Z. I had a prior for what I thought Z is probably like. And now you can see whether this distribution over Z's from Q is very, very different from that prior, right? And the idea is this serves as some sort of complexity measure. If I'm very close to the prior, then my distribution Q is probably not that complicated, because it's just like what I had assumed it would have been in the first place. And my assumption about the world is usually more simple than it is complex, right? So it's measuring some sort of complexity. And then this last term, this is the distance between my Q function and the posterior, like the true posterior, right? So this is a sense in which, oh, Q can be a proxy for my posterior, right? In some situations, if my Q family is large enough, it actually includes the true posterior, and this last term would vanish. But in general, this is not the case, right? In general, my Q, I can get close to the true posterior, but not exactly equal. And so there's going to be some distance between Q and the posterior. So you can see these last two terms are a little bit in tension, right? On the one hand, you are encouraged to make things simpler, right? You want Q to be kind of close to the prior. But on the other hand, you want the distance between the Q and the posterior to be small, right? So you want it to fit the posterior well without being too complicated. And right, that's why you have the difference in the signs too, right? Imagine you're trying to maximize the likelihood. You want this term to be small, right? Or no, did I mess this up? I might need to check. But then, yeah, I mean, this one for sure makes sense, right? Like you want the KL divergence to the prior to be small. I think maybe this also should be negative because I want my distance from the posterior also to be small. Okay. But then the point is, so yeah, the point is I have these kind of nice interpretation for my formula, for my kind of what had been my log P of theta. Like at the beginning, I was totally lost, right? I tried to sum over all the z's, and I couldn't do anything. But now I've converted it to an expression that I can make some sense out of, right? And now the last step about this point, about this expression is this posterior is actually very difficult to compute in reality, right? If we knew how to compute the posterior, then we wouldn't really be doing this whole exercise in the first place, right? We would already know what configuration is plausible. But we don't know what configurations are plausible yet, right? So we can't actually compute that posterior. So what you often do is you just zero out that term. Because you know that the KL divergence is always larger than 0, because there's a distance between things, so you can't have a negative distance between things, right? So when you ignore that, then you're left with this kind of simpler expression, and each of the terms in that expression are easy to compute. Right? The likelihood term is easy to compute. This Q function you know because you defined it. And the prior is also like usually some simple function. Okay. Okay, so now just this is a lot of stuff coming at you pretty quickly. Now I want you to try an example, right? Just to see, and forget about the math for a second. I want you to see if you understand the interpretation in terms of reconstruction error, approximation complexity, and approximation quality, right? And the way we're going to do this, think about, like you observe these points in one dimension, right? Now, what is Q? In this particular example, what Q is going to be is it's going to assign you to one of the two categories, like red or green, right? And remember, Q is a distribution, right? So we need to give it it's not just an assignment, it's not a fixed thing. It needs to be some probabilities of being one class or the other, right? So that's what the heights of the bars are, right? So here, the Q associated with this Z puts a lot of mass on the red mixture component, and a little bit of mass on green, but not that much. Kind of here, it's a little bit in between. It could be kind of either red or green, it's not sure. But over there, it's pretty sure that it's green. Right? So you think of these as for each of the z's, I put a Bernoulli distribution across these two categories, and my probability of that category is like the heights of these bars. Right? So this is one choice of Q. Right? So like in this sort of formula, I can just plug in that Q, and I can compute this quantity in closed form. Right? Or you can estimate it. Right? And then the bottom, so now this is a different configuration of Qs over these points. Right, so in this configuration, I just look at each point and I say 50-50 chance of being red or green. I'm not going to make any guess about which component really it belongs to. Right? So the question for you is, between these two options, which one has higher reconstruction error, and which of them has higher approximation complexity? Right? So basically, in which of these two do you have a higher expectation log p theta x given z? And in which of these do you have kind of a smaller distance from your prior, right? Or like a lower complexity, right? So I let you discuss this for a few minutes, and then I will listen to your explanations after then. So maybe discuss with your neighbors. But I should have clarified that my prior over the z's would be, say, like a 50 or an answer. And I can show this picture. It should help a little bit. Does anyone want to volunteer it? I don't have chocolates today. That's the main thing. Yeah, no wonder. Okay. I know a bunch of you got it because I was speaking to you in the audience. Okay. Yeah, it's okay. It's a little bit complicated to explain, so I'll just cover. And it's like the exact same picture. I wonder you didn't even notice at the same time. But okay, what's going on? Right. So it's like I wouldn't have any preference for one class or the other across all these. And then there was another good question I got talking to people is kind of, in this bound, like why are we doing this bound exactly, right? So I should have mentioned that too. The reason we have the bound, so first of all, we're dropping this because it's really complicated to compute. But second of all, this gives us sort of a proxy for that log likelihood, right? It's not exactly equal to it anymore, but it's close, potentially. If this is small, then that's close, right? So the idea is going to be, if you can make this lower bound really high, if you can find a configuration of the z's so that this q of z, this expectation over the q of z, is making this expectation minus the KL large, then you have a good chance of estimating the thetas on the left-hand side, right? Because right, you can basically jointly optimize the thetas and the z's. That gives you something which is a lower bound on your overall log likelihood. And then if you're maximizing the lower bound, then you're maximizing, or like you're increasing the thing that you're trying to get in the first place, which is this overall log likelihood, right? So that's why we're doing this in the first place. And then the explanation, so what's going on, kind of a lot of you see this. The second distribution has a higher reconstruction error. And why does it have a higher reconstruction error? If we want to be totally explicit about it, we can think about, so it's, what is the reconstruction error? It's an average over this likelihood across my given guess at what the Qs are like, right? So you need to think about, what does my likelihood look like if I have a particular configuration of the Zs, right? And in this kind of second case, where my configuration of the Zs, I'm not really making any guess about which class it comes from, kind of when you average over all those configurations, you kind of blur the differences between all the mixture assignments, right? So when I do the fit my means, I end up just fitting a mean that's kind of in the middle, and then I get likelihoods that are kind of similar for both of the classes. Right? Because it doesn't really see any distinction because I'm averaging over kind of assignments that make the points look all similar to each other. Right? So this is, since it has to spread itself out across all the points, it has higher variance. So when you look at the likelihood, it's just lower in general because it's all spread out. So, and since the likelihood is kind of a product of all the heights on these lines for these points, that product of the heights is going to be smaller than if I knew that these points were red and I knew that these points are green, then my likelihoods are actually quite high. And when I multiply those numbers together, they're going to be larger. Right? So my expectation of this log likelihood is going to be bigger. Right? So that's the reconstruction error part. So the idea, this one has lower reconstruction error on average. It has a higher expected log likelihood. And then the complexity part, kind of the idea is this is like a distance from your prior, right? Since this one is not really making any bets about which class you belong to, it's actually not that far from the prior, right? It's a very simple distribution. It's very naive, but it's simple. So it has that in its favor, right? Versus the second one, you're making a little bit more of a stronger statement about what you think the configuration looks like. So when you're a little bit more kind of direct about that, then this is a more complicated class than if you're just sticking with your prior, right? So that's the answer for that part. And I think, yeah, this is basically the same thing. This is going to be a new section anyways, so I think let's take a break.